Hey everyone, welcome back to another video in this series on quantum coding. So I will keep on the trend of discussing some theoretical aspects. So this is the third video in that small mini series where first I discussed single qubit gates, then I discussed the block sphere, and then now I will discuss multi-qubit gates. So I promise this is the last ingredient that you need for actually implementing quantum algorithms. And after this, we will straight away jump into the good stuff. So let's directly dive in. So now, instead of a single qubit, let's suppose we have two qubits. So here you can see I have qubit 1 and qubit 2. Now the combined state is basically an outer product of both of them. And since there are basically four possible states, because this one can have 0 and 1, and even this one can have 0 and 1, the combined state is a four-dimensional object. And it's an outer product. So outer product means the states get added up. So that's why in the representations that I discussed previously, I had something like 0, 0. So where this meant the first qubit and this meant the second qubit. So this is what outer product is. So let me just quickly go over it. So if I have A0 plus B1 and I want to do an outer product, so OP, and then I have C0 plus D1. So in this case, the result would be AC00 plus AD01 BC10 and let me see. I hope you guys can see this. And BD11. And because we have four states, 1, 2, 3, 4, now it's a four-dimensional object. That's why it's four, because you're considering all possible combinations. All right. Now, the gates that we saw in the previous lectures, we had single qubit gates. Now, you can still have those single qubit gates acting on those single qubits, but then their representation would be slightly different. And the reason is whenever you have, so when you had a single state, single qubit, your state would be some 0 plus something 1. But now, whenever you have multiple qubits, you should think of states as being these four-dimensional object. For 3 qubits, it'll be an 8-dimensional object. So whenever you have multiple qubit, always think of the state of the system as being product of all of them. Now, if they're entangled, it can't be written as a product, but then it's always a combined state. You should always think, whenever you have multiple qubits, only think of combined states. So now, in the case of this X gate acting on only the first qubit, we have to think of this X gate acting on this combined state where it only flips the first bit. So let me restate that again. Since this X bit is on the first qubit, the way you think about it is this X gate acting on this combined state. That's why it has to be four-dimensional again. It has to be a four-dimensional square matrix, and it only flips the first qubit. So the way you represent that is, again, as we saw, combined state is first times first outer product, the second one. So here you are only flipping the first state. That's why X is acting on the first one. And then I have an outer product times identity. Identity means you keep the state as is. You multiply the state by an identity matrix and it stays the same. So X is this, which we saw last time. And then the outer product is this, identity. So the way you should look at this product is multiply each element of X by this whole matrix. So this whole matrix times 0, we get these four zeros. This whole matrix times 1, we get this matrix back. This whole matrix times 1, we get it here. And this whole matrix times 0, we get a 0, 0 here. So this is the four-dimensional representation of X acting on the first qubit. Now, um, another way to think about it is think of the rows to be numbered like this. So this is how the rows are numbered. Um, yeah, and even the columns. Oh wow, it's a bit difficult in OneNote. Let me, yeah, 0, 0, 0, 1, 1, 0, 1, 1. Right, so let me just get this up a bit. Okay, so this first row represents 0, 0. Sorry, the yeah, and think of this as a transition probability. Think of these matrix elements as the transition from a state 0, 0 to 0, 0, or state 0, 0 to so the row state to column state. Now from 0, 0, you can go to what does 0, 0 become? Because the first bit gets flipped, it becomes 1, 0. So that's why the corresponding 1, 0, there is a 1. 0, 1 becomes 1, 1, and that's why the last element is flipped 1. 1, 0 becomes 0, 0 because 1 gets flipped, and 1, 1 becomes 1, 0, 1. So only because only the first element is flipped. That's how, I know it's a bit messy the way I explained, but I hope you get a sense of what these matrix elements represent. So this discussion was about an X gate acting on only one qubit. Now let's look at pure to multi-qubit gates, and there is practically only one important one. If there are some others, but then I will discuss them later when we actually need them. But then C naught is probably the most important gate that you will encounter a lot of times. So let me spend some time on that. C naught is basically a controlled knot. And the idea is that so let's say we have two qubits. One of them is considered the control one. So say the first one is the control and the second one is the target. So what C naught does is the target gets its bit flipped if the control is active. So let me restate that in simpler terms. So here the control is the first one and target is the second one. So what's going to happen is second is flipped only when first is 1. So the target is flipped only when the control is active. So let's see. So let's look what's happening here. If we have 0, 0 state, this will remain 0, 0 as the first one is 0. 0, 1 would again remain 0, 1. Now 1, 0 would become 1, 1 because since the first one is 1, so the second one gets flipped. So we get 1, 1. Similarly, 1, 1, second bit gets flipped again, becomes 1, 0. So this is an interesting gate that kind of works like an XOR. We had already seen its application. So this was used to create an entangled state. And let me just get into the theory, like just explain that again. So now imagine you have two qubits again, and you have a Hadamard gate here, and then a control knot. So let's try to calculate the state at the end. Suppose you plug in zeros, like simple zero states. That's how a system begins with. So this zero, after the Hadamard gate, becomes this state, 0 and 1 equal with equal probability. If you remember, H made 0 into a plus state. So this is what the plus state is, 0 and 1 with equal probability. So at this point, the state of the system is the first qubit, which is the plus state, outer product 0. So if I write it out, I get 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 0. Just add the 0 in here because it's an outer product. Now, when I apply the C naught, what happens? For this first one, nothing happens because the first bit is 0. The second bit, for the second element, the second bit gets flipped. So we get our entangles. So we get our entangled state over here, 0, 0, and 1, 1. And that's how we were able to generate this entangled state. Um, Now, this control NOT gate, you could also have it flipped where the target and controls are interchanged. But then the first bit would be flipped when the second is 1. So it's a straightforward generalization. And this is how a CNOT gate looks like. So again, you can, from this mapping, you can construct the elements. 0, 0 goes to 0, 0. That's why we have 1. 0, 1 goes to 0, 1. That's why we have a diagonal 1 again. And these two are flipped. So that's why we have something like this. So this is how you would, this is what a CNOT does, and which is like a truly multi-qubit gate. Since we had seen this before, let me quickly open the same file that I talked about before and show you this gate in action. So let's see, how do I do this? Right. So I got Visual Studio Code over here with um, with the same script I used to create entanglement. And let me go over the script again. So what we did was we created two qubit circuit with 2 qubits and 2 classical qubits. Sorry, 2 classical bits. And I applied the Hadamard on the first one, on the 0th one, and then a C naught, so connecting 0 and 1. Now, 0 represents the first element is the control, and the second one is the target. And then I basically measure these values out. So this is how my gate looks like. The first gets a 0. The first gets a Hadamard, and then I have this C naught, and then I measure my output. So circuits like this are always initialized with 0, so that's why I don't have to specifically set the initialization to be 0. And then I run this code on an actual quantum computer, and the output I get is, as you can see over here, the state 0, 0 and the state 1, 1 are the highest occurring states. Because the combination of Hadamard and the C naught creates an entangled state, so you will only see 0, 0 and 1, 1. You can see some minor quantities of the others, but this is just background noise. So this and this state are the most frequent ones, and that's how it should be. So this concludes this minor mini series on quantum gates, and next time we will jump into a full-fledged quantum algorithm and the theory of it, and also go and implement it. So I hope you enjoyed this video, and I will see you guys the next time. And please like and subscribe if you liked it. It helps me out and also gets the channel going. All right, see you guys next time.